So I'm going to do this talk in English because I can't really talk about technology in Portuguese. It's really hard to say every two words with some kind of buzzword. So let me know if you can hear in the back, or if you have any questions. I would love for you to give them at the end. I'm going to leave a lot of time for you to ask whatever you want. I always do demos, so I have 2 small demos for you today, and then at the end, feel free to come by. I'm going to be, after the conference, checking out a few talks. So if you want to hack on something, or show me something, or talk about more about certificates, I'm going to be around. Cool? So the title of my talk has an emoji, which I think is really adequate, because the audience that I talk about these days really is into Snapchat and all these other things. So I think I want to be more millennial, and I really want to connect with the audience. So mutual TLS in microservices world. Mutual TLS is obviously, for those of you, it's a security conference. It means mutually authenticated transport layer security, and it's effectively the way of using transport layer security with client certificates, server certificates, and authorizing each other. The baseline for this talk assumes that you know what TLS is. I'm going to talk a little bit about the details and about the advantages, but assumes that you know this. And so if you don't, please put your hand up, and I will very quickly explain what this is about. Onward. So a little bit before, wow, this was jumping way too many slides. Before I go into the talk itself, let me talk about why am I here and why I'm going to talk about TLS. So for those of you that don't know me, my name is Diogo, Mónica. I'm Portuguese, which is great. I'm an alumni from Technic, IST. I did my PhD in computer science. And then throughout my PhD, I was actually flown to the United States, to San Francisco, by a company called Square. Square is a startup that was founded by Jack Dorsey, the founder of Twitter. It's a small credit card reader that you plug on your phone. It can swipe credit cards. And essentially right now is moving $48 billion a year. I was the second person in security. I went there when we were 50, and I left when we were 1,300. I was there when it was a Series A company, and I left when it was a publicly traded company, and now it's worth $5 billion on the public market, stock exchange in New York. Throughout all of my experience at Square, the reality was that there were no open source or closed source tools that were adequate to actually have security for a payments company that was a startup and that was living after 2000. Everything that was built on top of HTTP and had really no security for us. So across my existence in the 4 years that I was at Square, we had to build a lot of software. And one of the things that we had to build, and that we did from day one, was we realized that we should not be using the network, or we should not be trusting the network. And so every single call at Square, every single service-to-service call, even to localhost, used mutually authenticated TLS with client certificates. It doesn't matter if it was on the same host, across switch, across data center, everything used mutual TLS. And so today, I'm going to go over a little bit on why we did this and how we did it and what are the advantages and disadvantages. After Square, I left to a company called Docker. I assume that by now you know what Docker is. I have a few stickers for your laptop. These are the small version of the stickers. They're really cute, so if you want them, come at the end. So my transition from Square, a lot of people ask me why I transitioned. The reality is, everything that I built at Square was always going to stay inside of Square. And at Docker, everything is open source. And so every single thing that I put in security into the container, all of you are going to inherit. And so I went to Docker, and the way that I looked at this was, well, why was it so hard for me to have a payments company and to actually have a secure infrastructure? Why wouldn't this be trivial for everyone? And so my job at Square right now, or at Docker right now, is effectively leading the security team and making sure that all the great stuff that is being used at scale for millions of users and for $48 billion a year is actually available to everyone else. So I've been at Docker for 2 years. Docker has, as you know, a lot of traffic. It's very successful as the effectively de facto standard for containers. And so we are also following this path, and we're building these things into our orchestrators, into our images. Perfect. So now let me actually talk to you about microservices. And I'm not going to describe what a microservice is. We're all sick of understanding and knowing exactly what the advantages and disadvantages of microservices are, but we all know the concept of monolithic application, bad, small little microservices that can scale independently, good. That's exactly what it is. If it's monolith, it's bad. If it's microservices and they're small, it's good. Whatever. But from a security perspective, there's actually some very concrete things and goals that you have to keep in mind while you're migrating your application from a big monolith to small components and microservices to use throughout your organization. The first one is that from a security team perspective, you have to think differently. Beforehand, if you had a monolithic application, all of the security, authentication, and authorization had to be built into the code. business logic and authentication, authorization, and security was all part of the monolith, because that's the definition of a monolith. Which meant that the security team did not have the ability to effectively create common infrastructure and common applications that all the teams could use and benefit. And so one of the goals for microservices is, if everybody needs secrets, if everybody needs TLS, if everybody needs a tokenization service, then you, as a security team, should build it and should provide to everybody else as a service. The second thing is that for a long time we've known, especially in the military, that least privilege as a principle is something that should be followed. But somewhere along the line we kind of lost our path, and the security people just started building firewalls and just saying, oh, let's block IPs and block ports, and now we have the crap that we have today. Unfortunately, or fortunately, microservices provide us another shot at this, and another shot at actually really starting to think about our infrastructures as least privilege, meaning that each service should only have access to the exact resources that it needs to do its business purpose. No more, no less. The third one is obviously better security monitoring. If you have smaller services, means that you actually have behaviors that are more contained. And instead of having an intrusion detection system that monitors the whole network of your company, or even monitors a whole host or a whole virtual machine, now with containers and now with small microservices, you can monitor one application. So it becomes a lot easier for you to do effectively recognition of malicious behavior and effectively pattern matching on what this application should be doing. And the final one is obviously the fact that with a ton of microservices, it's effectively impossible to do manual deployments, manual rollouts, manual scalability, and it's also impossible to do security. It's impossible to effectively issue manual certificates or trying to manage these things by hand, manually. And therefore, you need to automate the security of all of your development cycle, not just of your applications, but your production deployment in an end-to-end fashion. Okay, so given all of these goals, the major realization that I mentioned was that we have to stop thinking about layer 3 and layer 4, so network layers, as the security boundary. This is no longer true. It hasn't been true for 10 years, so we should stop insisting on buying firewalls. The reality is that in the previous world, we've all seen what's on top over there, which is effectively we have an internet, and then we try to segment and segregate all of these different regions and all of these different areas and zones by effectively just plastering a stateful firewall in between them. Well, it turns out there's a lot of problems with stateful firewalls. And if you actually go to any of the big players, a Facebook, a Google, so on and so forth, the only place where they're using stateful firewalls today is their corporate environment. Nobody uses stateful firewalls in production for the simple reason that they don't scale. There's really no stateful firewall over there that scales. Today, if you want to actually match the top of the line Arista switch in terms of bandwidth, and you want to have a stateful firewall that does layer 7 inspection, you effectively have to buy 200 Palo Alto firewalls or whatever vendor you have for each one switch. So effectively, you have to buy 200 times the cost of what, $350,000 just to actually keep at line rate with what a switch is. So the top is no longer feasible. And therefore, we come into a situation where the internet is effectively split between your internal network and your external network. And everything inside of your internal network is effectively one switch, a flat network, a flat hierarchy. The way that I think about this is, if you know of Google Beyond Corp and the effect of the ideas of exposing everything to the outside and having really good, strong authentication and authorization at the edge, what I'm calling this is effectively beyond prod, where you should not be isolating your production environment and thinking that it's behind a hard shell that is your firewall, and you should be doing every single service as if it was exposed to the internet. And the security requirements for a service to be inside of your network are the exact same requirements for it to be exposed to the internet. And this is effectively the model that you're thinking and you should be thinking. And so the reality, though, is if you're in this environment and if you have a flat network and if every service can talk to every service and your database is listening on the same network as your crappy WordPress blog for marketing, then you have a problem. And this is why we had firewalls in the first place. So the solution for this is obviously bring security to layer 7 and bring strong authentication and authorization to the application layer. Every single call between every single service of every single application of every single one of your data centers should be authenticated and authorized. So you should be able to know exactly what application is calling into you, and you should be able to know exactly what privileges that application is supposed to have.
And to do this, the major understanding or realization is you have a very difficult problem in your hands, which is every single one of your nodes in your infrastructure and your data center now requires an identity, right? And I don't mean like fancy like host name, like a cute host name like kitkat.docker.com, or I remember Technic who had like girl names, so Joanna or Beatriz.ist.com. That's not what I mean. I mean strong identities that are cryptographic and allow you to effectively have a way of identifying them in sharing confidential information. Why is this useful? Well, because if you have a strong identity, then you can obviously establish strong connections, secure connections, and then exchange things like secrets later on for your application. So it's obviously really useful. And identities should be per machine at least. We're going to talk a little bit about services and about how service and applications should also have their own identities, but the baseline is every single host or virtual machine that you have in your data center should have one of these. And I am using certificates there. I'm not using identities, but it's effectively the same. We're trying to go for an identity in general and something that identifies a host. But now, obviously, this comes to the old paradox. What came first, right? Was it the egg or the whale? And I know that a whale is a mammal, so just keep calm. But what came first? How do you bootstrap this? Yes, I have a machine, but how do I put the first certificate? What is the secure connection that bootstraps the trust of this? Sure, like if I can securely put a certificate and an identity in there, then I already solved the problem of the communication. So there's a couple of ways that you can bootstrap this whole thing, right? Well, there we go. There's a couple of things that you can bootstrap this whole thing. The first one is the understanding that you have a registration system, or at least you should have. The registration system is effectively what is responsible for adding new nodes to your network. And given a registration system, that registration system should be responsible for actually minting your identities for every single one of your nodes. How does that actually work in practice? Well, the way that I've seen done in the past, I've seen it done a couple of different ways. At Square, we had secure networks and VLANs and switches where a machine would be indoctrinated and then serial numbers would be verified from hardware to an actual registration authority that would have been manually added by a user when a new rack is actually put into the data center. And that network would effectively allow a machine to enroll itself in the registration authority by self-generating a certificate, a CSR, obviously with a component of a private key and a public key, submitting a CSR to a provisioning system, and effectively having a signed certificate come out of that. So the machine comes up, trusts the remote system to provide a certificate, and then uses that forever. Another way that we can do this is if you're using a virtual machine, you can bake this into the image. So technically you could bake this into the AMI. You could bake a public key, that is the public key that your system, when it's bootstrapped, is going to trust to actually do this dance and obtain its own certificate. So those are two ways. Another way that today people are using a lot is trust on first use. So effectively like a duck, the first thing that the duck sees, it's his mom. So even if the mom is a whale, now the ducks are all following the whale everywhere, right? This is effectively a system that is working pretty well today, and a system that works for a lot of web browser trusts like HSTS and things like that are a little bit used. HSTS, I know you can preload it, but they're based on the fact that you can do trust on first use, and then from the moment on, you trust all of these components. HPKP is another example of something that you're being told exactly what it is. So these are the ways that you bootstrap all of the trust on all of your nodes. And now that you have this, now I have to explain to you why I wanted certificates in the first place. Again, identities are not necessarily certificates, but certificates are really useful as identities because you can simply use mutual TLS to do everything else, to go from an identity to an actually secure channel that we can trust, right? And so now we actually have to go over the advantages and disadvantages of TLS. And mutual TLS has a lot of advantages, which are pretty obvious to most of you. The first one, it's supported by effectively everything. Everything these days has the ability of doing TLS communications and providing client certificates. The key material stays secret, both when you're actually trying to get an identity, so creating a CSR, sending the CSR, which is only public content, to get signed, but also when you're doing a connection, because you get to use Diffie-Hellman, and you get to actually use your public key components to prove who you are as a client and to prove who you are as a server. So there's never private key material that is actually going over the network. All of these things are computed independently on each side, the client and the server. And obviously it provides the CIA, so our confidentiality, our integrity, and our authentication to the process and the connection. Unfortunately, it has a lot of disadvantages. So it is incredibly confusing for engineers. So if you've seen an engineer trying to configure TLS or certificates, even on the non-mutual TLS case, just like serving a certificate that is correctly signed by a CA and doesn't present a browser red warning saying you have to accept this self-signed certificate, which we've all seen it, it's actually really hard for engineers to understand what it is, how to manage it. I've seen people put the private keys inside of their PEMs. I've seen all sorts of crazy stuff happen, right? And people obviously committing private keys to GitHub, which happens every single day, everywhere. The other thing is that if you're trying to do this on a machine basis, and if you have hundreds or thousands or tens of thousands of machines, that is a crap ton of certificates. How do you manage those? How do you rotate them? How do you distribute them securely? So this is a huge, huge problem that this system has. Another thing is that you are now running a PKI because you effectively need to sign certificates. So you need private key that needs to be maybe in hardware, at least protected in a way. You need to understand what revoking that private key means, or how rotating the private key happens, or what is your panic situation, something got compromised, press the red button, something has to happen. So you have to have organizational maturity to actually run a PKI successfully. For example, I didn't know if you knew, but certificate revocation lists, the CRL that TLS automatically, the majority of these clients use to check if the certificate that they're using is revoked or has been revoked, actually has an expiration. So I've been in a situation where some unknown mobile payments company's infrastructure goes down because the CRL ran out of and it was effectively expired. Right? Who would have known, right? Now I know, it's burned into my memory. Every time I go in and do any kind of audit or any kind of consulting, I go and check the expiration of the CRL or its existence in the first place. But the reality is that you think you're being smart by having a CRL, or instead of not having CRL and not bothering, you think you're being smart, but then you're bitten because TLS is, to the next point, completely unforgiving. If a CRL expires, if a certificate expires, I can guarantee you there's no amount of reboots or restarts of your service that is going to bring it back up. This is now how computers work with TLS. You reboot it and it's still down because it's just that unforgiving. However, this is actually the best that we have today. And so, given all the disadvantages, given all the advantages, we still should be using TLS because it's everything that we should be using. And have I mentioned that it's unforgiving? Because you really, really have to understand that the moment you turn this on, it's impossible to turn it off. Okay, so now let me talk to you about how we actually are solving this at Docker. Docker 1.12 came with built-in orchestration. What that means is that when you use Docker, effectively instead of just running containers and stopping containers on a local host, you actually have a full-featured orchestration system built in. So by just doing swarm init, you can create a manager, and by doing swarm join, you can join new workers to the swarm and effectively have a distributed system that runs all of your containers in a distributed fashion. And so when I was working on this project, I actually thought a lot about this problem of certificates, how to do the indoctrination, how to do rotation, and I decided, look, I really want to solve this problem once and for all, and for everybody else, at least for all the Docker users. So let me talk to you about a little bit about how we actually did it and how the system actually works. So in Swarm, there's two concepts of nodes. There's a manager node, which is really important. Managers are part of Raft. They have a quorum. You can add more managers. The usual number of managers is either 1 if you don't care about high availability, 3 if you can tolerate 1 failure, or 5 if you want to tolerate 2 failures. You can also have 7, but it's effectively a Raft quorum. All the managers are the highest privileged nodes on your cluster, and they're really small compared to all the workers. So 3 managers can run thousands of workers, which is the second kind of node that we have. The first thing that happens is automatically, out of the box, when you bootstrap this, you do swarm init, you get a CA for free. It is a self-signed CA. I'm going to describe how we do the bootstrap, but you get a CA for free. So the manager has its own certificate, has a certificate authority, and it's constantly starting to rotate the certificates. And I'm going to show you a demo of this. The second thing that happens is when a new node wants to join, what it does is it does a CSR dance, generates a public-private key, submits a CSR, and it gets a signed identity that is actually issued. Note that there's actually a token that is involved there, and I'm going to describe how the token actually allows us to authorize joining the cluster. So this is how a worker talks to a manager to get an identity. So at this point, both of those nodes have TLS certificates that allow them to use mutual TLS with each other. The third thing is obviously workers and managers are always identified by certificate. What this means is that the certificate actually has embedded on the OU and other attributes what the privilege of the node is in the cluster. So the certificate of a manager describes that this node is a manager, and the certificate of a worker describes that this node is a worker. Which means that there doesn't need to be a centralized place of authority when you say, these are the managers, these are the workers, because the certificates themselves prove who you are. Because they were minted by a certificate authority that says, no, this node is of this privilege. And then finally, you effectively have all the communications between the cluster that are using mutual TLS out of the box. You had to do nothing to configure it. And I'm going to show you how easy that is. I mentioned a token. So when a node wants to join a swarm, wants to join this orchestration in this network, it has to provide a specific token. And the way that we did the token was pretty interesting. It's not that complex. But the first thing is we started with a prefix that all tokens have that are common. And the easy reason for this is that your security team now has a specific string that it can search on CVS or on VCS, GitHub.com, etc. to see if any one of your developers actually committed a secret token into GitHub. So it just makes grep easier. That's all it's doing. The second thing is obviously a version. That's self-explanatory. But the third and the fourth are more interesting. The first one is actually a cryptographic hash of the actual root CA. What this effectively means is it turns the issues of downloading a certificate from all the CAs to all the nodes easier, just because now you only have to share this token. And this token allows you to ensure that you're joining the right CA and that you're bootstrapping, that you're downloading the root CA of the right identity. That's effectively how the bootstrap works. Once this token is shared securely, now you know that you're joining the right swarm because nobody can fake that SHA-256. And then it's a randomly generated secret that you can rotate at any time. And that secret is presented to the managers. The managers are in sync using Raft, so they all know what the current token is valid. And if a node presents a valid token, then it's authorized to actually be issued a certificate. So it's easy as this. We turn the bootstrap into sharing of a token that has a few characteristics that allow us to bootstrap the system securely. And so in terms of bootstrap, you have a worker. The first thing that the worker wants to do is to join the cluster. So it provides the token. It downloads the actual root CA. And with the token, the component of the hash checks if the root CA of the remote manager is actually valid. And if it is, it now knows that it's not joining a fake manager, that it's not being man in the middle, because the certificate that it actually got is the valid one. The second thing that it does, number two, is generates a public-private key, generates a CSR, and submits a CSR to be signed. And the manager doesn't trust anything from the CSR except the public and private key, and obviously all the attributes that are related to that. Everything else inside of the certificate or inside of the CSR is ignored, and the certificate that is issued by the manager from the point of view of saying, no, you are a worker. I am telling you you are a worker, and this is a certificate that you should be using, and they should be presenting everywhere else. And the third one is, after you retrieve the signed certificate, now as a worker, you can talk to any manager. And I don't need to actually put anything on the backend store because any manager that receives a TLS connection with this new certificate can understand that this is a node. And now the manager can issue a randomly generated identity inside of that certificate. So now we solved our problem. Every node that joins gets a randomly generated ID from the manager that is signed by a CA, and it can't be faked. So effectively, we bootstrapped our identity for all of our workers. In terms of rotation, one of the things that is really, really hard in TLS is the fact that you have to rotate these certificates. And how many of you haven't had downtime or issues with certificate expiration? Or how many of you haven't had to scramble last minute because the certificate's going to expire in 2 weeks? So one of the issues about TLS in mutual TLS is that revocation is really, really hard. So what people are doing is we're shortening the length of certificates from years before to 1 year, to 3 months, to maybe 1 month, to maybe 2 weeks. To, in our system, you can bring it all the way down to 1 hour. But if you have certificates expiring every hour for every node, there's no way in hell that this can be a manual process. And therefore, I needed to build in a good, very solid certificate rotation for you. So this is what we did. We no longer need the certificate, the token, to do the original bootstrap because you already have an identity. So what you do to rotate a certificate as a node is you connect to a new endpoint, you do mutual TLS, you prove that you own a certain identity, and now you get issued a new certificate with a slightly longer expiration time. So it's effectively revalidation of certificates as time goes on because you can do mutual TLS. And if at any point you're down for long enough for your certificate to expire, then you're effectively out of the cluster. That is totally indistinguishable from an attacker stealing a certificate and then trying to use it sometime in the future. So automatic certificate rotation is handled for you.
Why are you increasing the time?
we're effectively revalidating and adding a new expiration. We're not increasing the time, it's just reissuing a new certificate. And we obviously wanted not to have you depend on RCA. The reason why we have it is so Bootstrap is absolutely trivial. We wanted you to also be able to take these to your companies and support an external CA. So you can't just point the managers and say, manager, do not use your local certificate authority, just use this remote one that I have. So if you are sophisticated enough, and if you have a company that already has a certificate authority, then you can effectively use all the managers in all the same path. Think of us as last mile delivery for the certificates that come from the backend. And we still manage all the rotation of all of the internal nodes. And the only thing you have to expose is right now a CFSSL kind of API for certificates on the backend. And we do everything by just forwarding the CSRs back and forth. So effectively, we allow you to run automatically out of the box with a CA, or you can bring your own. So now let me show you how easy this is to set up in practice. Let me show you SwarmKit. SwarmKit is the base component that is actually imported into Docker. So at Docker actually imports some external components. They're all open source on their own. SwarmKit is a toolkit for you to build distributed systems that has all of this, and now it's used into Docker to actually provide this. So I'm going to sit down. First thing that I'm going to do is I'm going to go over here. Is this big enough? Okay, I can make it a little bigger. Cool, I have 3 terminals. So this is SwarmKit. This is effectively a slightly different branch of master. The only difference over there is that I'm rotating every certificate every 5 minutes, every 5 seconds, instead of actually respecting the validation time. The way that I do rotations in Swarm, by the way, is you define what the rotation period is. Imagine 1 week. And then what I do is I renew the certificate from 50 to 80% randomly assigned within that 1 week window. And the reason why I do that is because thundering hurts. I don't want all certificates. If you issue 1,000 nodes and you bring up 1,000 nodes at the same time, they're effectively going to have their first certificate issued on the same 1 minute or 2 minute or 30-minute window. So by doing randomness on the actual rotation, I get to uniformly distribute them across time. And as time goes on, I will not have spikes of issuance of certificates, and I won't have my managers go down because all of a sudden everybody decided to rotate their certificates. So these are the small details that I've had to do in the past, that I've had downtime for in the past, and that I bake in as very opinionated defaults into the actual Swarm. So the only difference here, again, is this is SwarmKit for master with 5-second rotation window. So the first thing that I'm going to do, and Docker is a lot easier than this. This is like the underlying component, so it's a little bit harder to digest. But the first thing that I'm going to do is I'm going to run a node. This is going to be the first manager. This is going to be the manager that, when ran, is going to create a CA, issue its own certificate, and start rotating its own certificate. For now, it's going to be isolated. It's going to be a manager of 1 with a network of 1. So once I run this, you can see a bunch of things here. It actually created a certificate. It scheduled a certificate renewal. And now every 5 seconds, you're going to see a new certificate with a role manager being issued. So you see these certificates are being renewed, and all of these are being scheduled, and it's taking care of itself. Okay? So now this network is not very interesting, right? Because we have 1 node, and it's rotating its own certificates. So what I actually need is to join a new node to the network. And for this, we need a token, right? We need the secret token that I showed you how it was composed. So what I'm going to do is I'm going to inspect the cluster. And I'm going to do swarm CTL, which is a controller, inspect the default. And it's going to give me join tokens. 1 for the manager, 1 for the worker. So if you want to join a worker node, you just provide the token. If you want to join a manager node, you just provide the manager token. Everything else is transparent for you. And you can also do promotions and demotions as I'm going to show you. But for now, let's copy this worker token. We have it. And now let's join a new node. And how do I join a new node? Well, it's as simple as saying, create a new node, join to this address, and this is your join token. And the join token is the thing in white. So once I press enter, now I have 2 nodes in our swarm, and you're going to see that this node is an agent. It's actually a worker, and it's renewing certificates every 5 seconds. You see the role, swarm worker, and every 5 seconds it's renewing certificate automatically. And I can show you this in 2 ways. Number 1, I'm going to list the nodes of the network. We have a manager here, which is the first thing that we created. It has a certificate authority. It is the one that is responsible for issuing certificates. And we have a node that is effectively not doing anything here, and it's actually not responsible for running anything right now. The cooler part is if I do this. If I do OpenSSL inside of a watch, and now we're actually looking at certificates. So now you're seeing what you were expecting to see. You have a node that is a worker, and therefore the OU of the node is worker. The OU is here. This is what we expected because we're expecting the certificate of the worker. The second thing that we're expecting is a randomly generated identifier that is going to identify this node for the lifetime of the node in the cluster. And so every 5 seconds, you see the certificate rotating. But note the portions that are actually being rotated, which are the portions that show in white. The only thing that is being changed is obviously the public key, private key material, and the serial number of the certificate. Because all of the other attributes are attributes of the node. The identity is constant, the worker is the role is constant, everything is constant except the actual certificate. So you see that this is the actual rotation that you would have to do manually, happening every 5 seconds for every single node in the network with no connections dropped. You could have 10,000 nodes connected to a manager, and the manager can rotate all of the certificates from under the connections, and nothing gets dropped because everything is being handled in a transparent fashion and in an atomic fashion. So this is really cool. But now let me show you that this is actually working. So I'm not going to stop this watch. I'm going to go to a new window over here. And I'm going to do the following. I'm going to do node LS. We see our manager. We see our worker. And I showed you on this watch that this OU is worker, correct? Because it's a worker node. So what I'm going to do is I'm going to do something. I'm going to do a promotion. SwarmKit and Docker has the concept of a promotion, which is, as I told you, managers, you can increase the number of managers to have a high availability cluster. But we made it super easy for you to build this. And so you can promote any normal node to be a manager or demote any manager to be a worker node. And when you promote them to be a manager, now they become privileged. You just replicated your CA, you now have a high availability CA, and you have a high availability system because they're all participating in a quorum. So the moment I promote this node by providing the ID, the thing that we're going to see is, we're going to see this changing. OU now is Swarm Manager. Nothing else changed, but now the privilege of this node in the network is Swarm Manager. And it keeps rotating the certificate every 5 seconds. And we can actually go back and actually just demote the node and say you can no longer be a manager. And at this point, it no longer has any manager privileges in the actual cluster anymore. And it just got demoted to be a normal worker. And you can do this transparently, scale up and down, and all the certificates are always being rotated, and the identities are being taken care of this for you. So you never have to worry about certificates. If you notice, we did 2 things. We needed a init and the manager, and we did a join and a worker. And from this moment on, everything else is taken care of for us. So why is this important? Well, the reason...
What happens if the manager crashes?
If the manager crashes, no certificates can be renewed. And this is why you should have multiple managers, because if you have multiple managers, then you have a high availability CA.
You don't have automatically a worker to be promoted to...
You can't be promoted because a manager has to promote you. Because if a worker could promote itself to a manager, then the worker would be a manager.
Yeah.
So from a security perspective, workers are completely unprivileged, which is, by the way, I follow least privilege here. The worker only has access to the resources that the worker needs. If the worker gets scheduled a container, it only has access to the secrets, the resources, the IPs, and the code of the containers that it needs to run. It doesn't have access to other networks, it doesn't have access to other images, it doesn't have access to anything else. Only the managers are privileged. And I'm actually going to go forward with this, and I'm going to go least privilege all the way. I'm going to make the managers eventually untrusted. So I'm going to make the workers not even be able to trust the managers, such that the manager can force the worker to run arbitrary code. Anyway, from a perspective... Go ahead.
How does a worker authenticate against a manager?
It uses mutual TLS. It has a certificate, connects to an endpoint, presents a client certificate, does the dance.
No, in this moment, you create a manager, then you create a worker.
Correct.
How does it...
Token.
Why don't I create a worker myself?
Because you don't have a secret token. The secret token has a component that is secret that only you have, and that only you provide it to your Amazon, CloudWatch, whatever, or to the thing that scales your nodes, and only that token is allowed to actually join new nodes into the network. So that's effectively a secret, randomly generated code that nobody else has except you. And that's how the initial authentication goes.
But you run a program, a list that showed that goes, right?
No. So yeah, on the manager, with the manager privilege. So if you have access to the API of the manager, and you're an authenticated administrator with root on the node that is running the manager, then you effectively can list the code. If you were a worker, I couldn't list the code. Perfect. So now, at this point, let's wait for the end then.
Okay.
At this point, we effectively have workers that have their own identities. So every single manager and every single worker has its own certificate that it can participate in the system and say, this is the random ID that I am, and this is the privilege that I have in your network. But this is not what we want. This has always been about application identities. This has always been about applications and services connecting to each other. So what we actually want is not one node, one ID. We needed one node, one ID because we want one app, one ID. What we actually want is your orchestration system to provide you automatically identities for every single one of your applications automatically. So what should be happening is you have an orchestration system, you deploy an Nginx, you deploy a proxy, you deploy your Ruby on Rails application, you deploy whatever it is. And your orchestration system should be responsible for getting a certificate with the properties of your application and securely deliver it to your node with the certificate of the node. So now these certificates that we built for nodes were just a way to bootstrap what we really wanted, which is every application has its own certificate with its own properties, exactly like the nodes have, and everything is rotated automatically. This is the holy grail. This is the square model. This is mutual TLS between all the services. And so we should be using mutual TLS for every single service authentication. And this effectively removes all of the needs for your firewalls and allows you to have flat networks because you're effectively exposing TLS, which is the same thing that you'd expose to the outside in the first place. So you already have the same surface of exposure and you're actually concentrating it into one system of authentication and authorization. The way this works is in the CN of a node, you have a random ID that describes the node identifier. In an application, the CN describes what the application actually is. So in this case, you have a Go app that is called API01. For example, it's a payments API or it's some kind of authorization API. And then you have a database, which is MySQL, and it has DB01. These names have meaning. The moment this Go application wants to connect to the database, it connects to DB01, and it will verify that the mutual TLS handshake is providing a certificate for something called DB01. It can't DB02, can't be DB02, can't be DB03. No other application or service or node on the network can fake that because no other application has that exact certificate. And now that we have authentication on the applications, we can go even one step further and we can actually have authorization. So it's not just about me knowing that I'm connecting to a database or the API knowing that it's connecting to Redis. It's really about knowing what kind of properties the person or the service that I'm connecting to has. So we know that this API has access to this DB. Sure, we know the identities. But we also want to know what kind of credit card or what kind of database is it and what kind of environment is it in. For example, this case, that database is a production database. I should not let my API connect to DB01 in staging because they're totally different systems. And I also know this is a credit card database on the OU, the organization. So if I connect to DB01 on another OU, this should not work regardless. And if you extrapolate from this, you can now have something really cool. We built something called Guarddog, which was a framework that, framework that was across all of your applications. Everything was transparently taken care of for developers. Developers had to create one file to have mutual TLS work. The moment a file like this was created, they were describing how their application behaved within our network. Number one, they were describing that the resource user /user can only be accessed through a GET, and it can only be allowed by those three kinds of applications. So if there was an application that wasn't web, fulfillment, or payments, it could not access this endpoint. The same thing for post on user, the same thing for delete on user. So I just restricted that the only application that can delete users is the web application. And so this ACL is using the properties of the certificates of the services, which in turn is using the properties of the certificates of the nodes to actually have a secure chain of exactly what your application should be doing. And by the way, this does not replace higher level tokens with attenuation and macaroons and things like that. What this replaces is it totally replaces your firewalls and allows you to do microsegmentation to the HTTP verb, all reliant on self-regenerating and rotating certificates that are handled for you automatically. So now we need one more thing for this to succeed. We have a crap ton of certificates. Now we need a sane way to get them to the applications. And this is where I get opinionated again. And let me show you a demo of what we're actually building into Square and something that we just merged on Docker Master. So we go back to our actual demo. We still have our certificates rotating in the background. We have our worker and our manager. And what we're going to do here is I'm going to create a secret. I'm going to create secret create. This is kind of big. But what I'm doing here effectively is I'm echoing some kind of string into a command called secret create Diogo txt. Okay? So now I have a secret, and I can show you that I have a secret by doing secret ls, and you can see that I have a secret that was created, has a certain size, and has a certain digest. So what we created with Docker was we created a secret command that allows you to add secrets, remove secrets, and associate secrets. So if I am to create a service, service is the concept of containers in Swarm. You're not running one container. You're running a service, which could be Redis, could be MySQL, could be whatever, and then you can scale it with multiple instances or lower instances. So if I create a service, if I do service create, you can see here two things that are interesting. Number one, I'm going to do service create. I'm going to say that this service has 3 replicas. The name is test1, and it's an image that is Alpine. It's a Redis Alpine. So I'm running 3 instances of Redis, and I'm saying that I need secret Diogo txt. But more than that, you can actually say, I need secret Diogo txt, but inside of the actual container, I want to expose it as a file called diogo2.txt. So if you run this, you effectively have a service. I can show you that we have a service called service ls. This is our service. And now if I do inspect of the service, we actually see that the service has 2 secrets. It has Diogo txt exposed as Diogo txt and Diogo2 txt. So what this actually means is that inside of Docker, when you're running Docker, you're effectively going to have this. Once you run a container of Redis, you're effectively going to have a secret called under var secrets in whatever name you want. In my case, it was Diogo txt. In this case, it's AWS credentials.yml. The way that this works is it's a TIMPFS that is created inside of every single one of your containers and only contains the secrets in memory. These secrets are never sent to disk. They're never written to disk. And they're dynamic. They're created when your container is created, and they're only sent down to the worker nodes that actually need to run these containers. No other worker node can have access to any other of these secrets. So now we have a sane way of distributing secrets that magically appear as files. This could be your certificate.crt or certificate.key or whatever it is. They appear as a file. You can load it on your AJ proxy, you can load it on your Nginx, you can load it on your Postgres, you can load it on MySQL. It's effectively just a file that you have access to. And by the way, you can also control privileges and what users they're presented as the files in memory, whatever it is. But now that you have the actual way of distributing the secrets, and you have these certificates that are automatically being generated, Swarm will, in the next version, create for every single one of your applications, by default, a certificate that you can use, that is signed by the CA of the whole Swarm, and that everybody has access to. So effectively what I'm telling you is, the next time you want to run, or when we release the next version of Docker, the next time that you want to run an AJ proxy that does mutual TLS for your application, or the next time that you build an API and you want to authenticate your API, the only thing you have to do is you have to point it to var run secrets service.crt service.key, and you have to verify that you actually have an ACL that matches the properties that you want. That's it. You get your certificates, they're rotating automatically for you, they have the description of the services that you describe and that you set up, and everything else is taken care for you. With these 2 things, service certificates and secrets distribution, you actually finally can get to mutual TLS by default in your infrastructure. So that was my talk today. Thank you so much. Feel free to ask me any other questions. More questions? Go ahead.
What is the lifetime of the certificates?
So, yeah, you get to define them. By default, nodes exist for 3 months.
3 months?
3 months. And you can turn it all the way down to 1 hour. The reason why I didn't allow you to do less than 1 hour is because TLS has a big problem, which I actually didn't describe or didn't say that I should have said, which is it uses wall clocks. And wall clocks are out of sync very often. So in the original POC and the original code that I did, certificates could be turned all the way down to 15 minutes. But immediately we noticed that when we were deploying across multiple clouds, AWS, DigitalOcean, Azure, Google Cloud Platform, and we had like 1,000 nodes with a swarm, all rotating certificates, immediately we started seeing issues where nodes would be dropped off because 15 minutes, they would have clock drifts that would not allow them to rotate in time. And because they thought the certificate was going to be available for a longer period of time, but the manager on the other side said, nope, this certificate is expired, I no longer want to touch it. So we effectively allow you, or we prevent you from shooting yourself in the foot, and I made the call that 1 hour is enough for you to have this. If you want to be more conservative, do a week.
So default 3 months. And what's the key length of the certificates?
The key length, everything is using CDSA. It's the only thing that I'm supporting right now, and it's P256. for all the certificates that are being issued. And one of the reasons why this is P256 and not 384 or 512 is because all the certificates can be rotated every 3 months, and all the certificates can be rotated every hour. So if you are actually want to be paranoid, you don't have to be paranoid about key length. You can be paranoid about certificate duration, which is actually something that I prefer. For the reason that in Go, P386 and P512 is not ASM optimized. So it's going to take you 20 times more to do verifications and issuances.
That was the purpose of my question.
Correct. So I use 256. You should control your security level by controlling the time of certificates instead of controlling key length. In the future, as soon as assembly comes for P384, I'm going to up the CA and up every single certificate to that. And then it's also a configurable parameter. But it's, again, like I made some super reasonable assumptions. So by default, you have to care about nothing. You spin up a manager, you join nodes, and you never think about it again. More questions?
How do you handle the name resolution of the nodes and the manager?
Okay, name resolution of nodes and managers. So Swarm actually does that for you. So the moment you create a service, you already have an internal DNS resolution within all of your containers that actually allow you to have name resolution automatically. So there's a DNS server that you query for DB1, and DB1 sends you what the IP address of a container is. And we also have a routing mesh. So it really doesn't matter. So we use different ports for different services. If you hit, imagine that you have 100 nodes, and you have a service running on 20 of them on port 8080. You can hit any of the 100 nodes. It doesn't matter if they're running the service or not. Internally, what I do is if I receive a request on port 8080 on a node that is not running that service, I do internal routing mesh, and I forward that to the actual nodes that are running the service.
How does that handle with the receiving end that receives the answer from a node that he didn't ask for?
So actually, everything is transparently. It's essentially triangular routing. So you effectively see the original IP address and you receive from the original IP address. From the perspective of the caller and the receiver, it's effectively indifferent. It's like the request comes directly. But that's a great question. Other questions? About Docker, about certificates, about the security of services. So secrets are coming for Docker 1.13, and then service identities are coming for Docker 1.14. So as of Docker 1.14, you're probably going to be able to just run a container and then list var run secrets, and you'll have certificates there for you that are ready to use. Perfect. I'm going to be here at the end. Feel free to ask me any other questions. Thank you so much.